Okay, we're moving on with our regression analysis, and we've been looking at ways to assess the fit of the regression model. So we're looking at different quantities such as the residuals, the standard error of the estimate, and the R-squared to determine whether the regression model fits the data well or not. And so another way to do that, to look at and assess the fit of the model, is to look at the slope and conduct a hypothesis test. The slope is very important in the regression model, more important than the intercept. When we look at our estimate, B1, the slope is our rate of change for every 1 unit change in X. So when we test the parameter beta 1, then that's the slope parameter, we can then determine whether our predictor X is statistically significant in predicting Y. So we do that with this test. There's 3 ways it can be done. The first one is the null hypothesis is beta 1 equals 0 versus the alternative hypothesis beta 1 does not equal 0. And so we're just checking to see if it would be significantly different from 0. And this would be the 2-sided test. Or you can determine whether there is a significant positive relationship between the 2 variables. And when I say relationship between the 2 variables, I'm referring to the X and Y, independent and dependent variables of our simple regression model. In this case, the alternative hypothesis beta 1 would be greater than 0. The third and last case would be to determine whether there is a significant negative relationship between the 2 variables X and Y. In this case, the alternative hypothesis beta 1 would be less than 0. The null hypotheses are always beta 1 equals to 0. So we then calculate the test statistic and then get from the test statistic, get the p-value, and then make a decision. So it follows the same set of rules for the hypothesis test. So the test statistic here is a t-test statistic. So we can look at the t-table to get the p-value. The numerator is the estimate for the slope, B1, and the entire denominator here, that is called the standard error. So everything in the denominator is the standard error and the standard error of the estimate. It is in terms of the standard error of the estimate S sub e divided by the square root of the sum of the squares for the x's. So if we were to carry on with our online example using the support chat feature with our 5 customers and the online sales, we can conduct the test for the slope beta 1 equals 0. We'll make this a 2-sided test. Beta 1 does not equal 0. That's our alternative hypothesis. And then we can just plug in our values for t. Our B1 we calculated as being 0.519. And we also calculated S sub e, the standard error. And we got the 4 of the model, so that would be 4.38 divided by the square root of the sum of the squares of the x's, which is the square root of 4480. So that ends up being 0.519. That is our B1. That's our slope estimate, or coefficient if you want to call it, and for the slope. And our denominator, I want to show this separately here because its value is equal to 0.06544. So if a question asks what is the standard error of the slope estimate, you would put 0.06544. Okay, all that ends up being, we divide that out, it would be 7.93. So over on our table, I already have this set out here. If we look at 4 degrees of freedom, right here, because we had 5 customers, we subtract 1, that gives us 4 degrees of freedom. So we look at the 4 degrees of freedom row, and we can see as we go from left to right, our values are increasing. So our 7.93 would be way over here. And if you look at the top row, the t is 0.1, 0.05, 0.025, 0.01, 0.005, 0.001 is our smallest value. So you know that if we keep going in this direction, we're going to get smaller values. So that means our p-value is smaller than 0.001. So we can take that result here and go our p-value is less than 0.001 based on this statistic here on the table. So our decision here would be that we would reject the null hypothesis. So we would reject the null hypothesis and accept that it is different than 0. And so that value 0.519 is statistically significant. And what we would say then is that the predictor x, which was in our case, it was the time spent using the online chat feature, would be statistically significant in predicting y, the online sales. Okay, so that's how you know if your x value is statistically significant or not, is by doing the test for the slope. Okay, we can also calculate a confidence interval for the slope. So in this case, we already have the slope value, 5.519 plus or minus. Now that t value, what should we use for our critical value t? So that would be, if we want to do a 95, 95 is usually the most common, so we'll do a 95 here. So 95, that would be a t of 0.0. We would want to look up a t of 0.025. Let's go back to our table. We can find what that would be on 4 degrees of freedom. And so here's our t of 0.025. We're going to use 2.776. So we'll come back. 2.776. So 2.776, and the rest, remember all of this in the brackets there, that is the standard error of the slope estimate. So that would be 4.38. We've calculated, just to remind you, we've calculated all these values in the previous slides on previous videos. That gives us 0.519 plus or minus. The margin of error is 0.1817. Remember, this whole part right here, this little part right here, was equal to 0.06544. So that was the standard error of the slope estimate. All right, so moving along, that means that we have a value 0.3373. That's our minimum value, to 0.7007. So notice this is our minimum value. Think of the number line. This is our maximum value. Notice that the value 0 is excluded. It is not within that range. It's out. So in other words, it's outside. So that means that we would reject the null hypothesis that 0 is plausible. And we would say that it is statistically significant. So this is consistent with the result of having a small p-value and rejecting the null hypothesis, right? We are rejecting the null hypothesis and accepting the alternative hypothesis that it is different than 0, which then means that the predictor x variable is statistically significant in predicting the y, which in our case was the online sales. Okay, so in the next video, we'll look at how this looks with a computer printout.